Good morning student. Today we are going to discuss a topic from unit 1, partial derivative and maxima and minima. So this is quite related to total derivative. In total derivative we have one independent variable and one dependent variable. But when we have multiple variable in any function, we can do partial derivative. And when we are solving partial derivative, if you are taking derivative with respect to x, at the term y and z will be constant, and similarly for the others. So partial derivative help us to find the derivative with respect to one particular variable, keeping other constant. So procedure to find the derivative is similar like total derivative. The only difference is here partial derivative. Now as the name says, the name is partial derivative. Partial means we are taking derivative only with respect to one variable, and at that time the other 2 or 3 whatever are the independent variable, they will be constant. So you can see here definition is, if a function depends on multiple variable like f of x comma y, here f depends on x and y, so f is an dependent variable, x and y will be independent variable. Or if f depends upon 3 variables x, y, z, f will be dependent variable, x, y and z will be independent variable. Then we will calculate the partial derivative. How function changes, will change only in with respect to x, or with respect to y, or with respect to z. If you are taking derivative of f with respect to x, y and z will be treated as constant. If you are taking derivative with respect to y, at that time x and z will remain constant. Similarly, if you are taking derivative with respect to z, at that time x and y will remain constant. You can see these are symbol notation for partial derivative. So this sign is known as del f by del x. So this is partial derivative of f with respect to variable x, and this is pronounced as del f by del x. At that time, similarly, if we are taking derivative with respect to y, this will be known as del f by del y. So at the time when you are taking derivative with respect to x, y will be taken as a constant, and when you are taking derivative with respect to y, x will be treated as a constant. Let us see a simple example on the same. Let f of xy is a function x square y plus 3y. So here f is an dependent variable which depends upon two independent variables x and y. Let us find derivative, partial derivative of f with respect to x. So this is del f by del x. Taking y as a constant, it will be x square plus y. This is x square y, sorry. So y is constant, it will remain as it is. To find derivative of x square, we will apply the formula to find derivative of x raised to power n, which is nx raised to power n minus 1. So it will become 2x. The derivative of f with respect to x, partial derivative is 2xy. Similarly, partial derivative of with respect to y. And now when you are taking derivative with respect to y, at that time x, any term having x will be treated as constant. So here x will remain as it is. Derivative of y raised to power 1 with respect to y will be 1, plus 3 is a constant, that will be as it is, and derivative of y with respect to y will be 1. Further we have chain rule. Just like we used to apply chain rule in total derivative, we can apply chain rule in partial derivative when function depends upon two variable p and x, and this function f depends upon two variable p and q. Further, p and q depends upon variable x and y. To evaluate derivative of u with respect to x and y, we have to apply here chain rule. We will use a chain. So here u indirectly depends upon x and y through p and q. To find del u by del u, we will write this formula that del u by del x is equals to del f upon del p into del p by del x plus del f by del q into del q by del x. Similarly, to find derivative of u with respect to y, it will be del u by del y is equals to del f upon del p into del p upon del y plus del f upon del q into del q upon del y. So f depends upon p and q, which further depends upon x and y. So we are using here chain rule to find derivative of partial derivative of u with respect to x and y. Here is a simple example. If u is equals to f of y minus z, comma x minus z, z minus x, comma x minus y, we have to prove this is equals to 0. So what we will do here, let us consider that y minus z is p, z minus x is q, and x minus y is r. So u will be function of p, q and r, and we have to prove that del u by del x plus del u by del y plus del u by del z is equals to 0. So we will apply here chain rule. So del u by del x will be equals to derivative of f with respect to p and derivative of p with respect to x plus partial derivative of f with respect to q into partial derivative of x with q with respect to x plus partial derivative of f with respect to r into partial derivative of r with respect to x. Now p is y minus z, its partial derivative with respect to x will be 0 because there is no term having x. So y is constant, z is constant, and derivative of constant is 0. Further q is z minus x. Derivative of q with respect to x will be minus 1. Z is constant, derivative is 0. X is 1, so it will be minus 1. Similarly, derivative of r with respect to x will be 1. Now here put the value. Ux is 0 into f of p plus minus 1 into f of q plus 1 into f of r. So 0 term will eliminate. This will be minus f of q plus f of r. Similarly, using the same process, we will calculate derivative of partial derivative of u with respect to y and partial derivative of u with respect to z. In the end, we will add all these three equations. It will be cancel plus minus term, minus f of p plus f of p cancel, plus f of r minus f of r cancel, minus f of q plus f of q cancel. So each terms are with plus minus sign, they will cancel each other and result you will get 0. Hence del u by del x plus del u by del y plus del u by del z is equals to 0. Now why do we use partial derivative? They are useful in multivariable calculus. When we have more than one variable on which function depends, we can treat only one variable which is changing and other as constant, and it makes our calculation easier. Optimization of maxima and minima problem, we can use it, and in machine learning, physics, in physics we are using partial derivative in heat equation, motion equation and waves equation. Then further in economics, to find the profit of any function, to find the cost of many with respect to many variables, we can use partial derivative. So whenever a function depends upon several variables, more than one variable, we are using partial derivative. It helps us to understand how each variable is affecting any particular function. So further we have here maxima and minima. In this section we can see this is any curve. It has an absolute maxima, this is absolute minima endpoint, and this is local minima, and this local minima is this, and this is local maximum. So you can see the extreme points are giving at maximized value, so these are known as absolute, and this is local minima. There are 2 points A and B where f has local maximum, that is f of a comma b is larger than all the values nearby of f of xy. So the larger of these two values will be known as absolute maximum. So maximum value will be known as absolute minimum and absolute maximum. Similarly, the minimum, smaller of the minimum value will be known as absolute minimum. So this is the definition. A function of two variable has a local maximum at a comma b if function at point x comma y is lesser than all the point nearby. This is the concept of basically a disk. If we have a disk of a comma b, so the value at points nearby a comma b should be lesser than this. then the number a comma b is called the local maximum value, and if this is greater than this, then this is known as local minimum value. Then we have Fermat's theorem for functions of two variables. If f has a local maximum or minimum at a comma b and the first order partial derivative of f exists, then that we can find the stationary point by taking that first derivative equal to 0. Further we have critical point or stationary point. A point a comma b is called a critical point or stationary point if partial derivative at point this is 0. So how to find out this critical point? Find partial derivative of f with respect to x, find partial derivative of f with respect to y, take that equal to 0, solve those equation, you will get the point, and that particular point will be known as a critical point. So these are the further things for the single variables. Now let us see this example we have. Let f of x comma y is x square plus y square minus 2x minus 6y plus 14. Let us calculate its partial derivative with respect to x. All the terms having y will be treated as constant. So derivative of x square will be 2x, y square 0, minus 2x derivative is minus 2, 6y is 0, 14 is 0. Similarly, we will calculate partial derivative of f with respect to y. Derivative of x is treated as constant while taking partial derivative with respect to y. So this term will be 0, this will become 2y, again this has x, it will be 0, and this will become minus x. So these partial derivative are equal to 0. When you are taking this equal to 0, 2 will be common, it will be x minus 1 is equals to 0. So the first point you will get is x is equals to 1. And here when you will take this derivative equal to 0, take 2 common, it will become y minus 3 is equals to 0. So the only critical point here is x is 1 and y is 3. So this is our critical point. Now you can make this equation by completing square. This is x square minus 2x. This could be x square minus 2x plus 1 square. It can become x minus 1 whole square. Similarly, here we have y square minus 6y. 6 can be written as 2 into 3 into y. So 2ab, a is y square, 2 as it is, b is 3 square, which is 9. So you can break this 14, 1 plus 9 plus 4. 1 will go along with x square minus 2x plus 1, which will become x minus 1 whole square. 9 will go with y square minus 6y plus 9, which will become y minus 3 whole square, and this will be 4 plus x minus 1 whole square plus y minus 3 whole square. So this will become this kind of a parabola which has this point, since always any whole square is always positive. Whole square of any number is always positive. So it doesn't matter what is the value of x or y here, this will be always greater, and f of xy is always greater than equal to 4 for all values. Therefore f of 1 comma 3 is a local minimum and absolute minimum also for this, because there is single stationary point, there is no other point to check absolute. So local minimum and absolute minimum in this question is same, hence you can see this is in paraboloid, and this point is called the local and absolute minimum of this paraboloid. Then this is a method to find maxima and minima using second derivative formula. So what we used to do is, suppose the second partial derivative of f is continuous, is find the first order partial derivative with respect to x, take it equal to 0. First order partial derivative with respect to y, take that equal to 0. Then derivative of this is take second order partial derivative of with respect to x with respect to y and x with respect to y. Then what is d? Just like discriminant in case of a quadratic equation, d is multiplication of second order derivative with respect to x into second order derivative with respect to y minus derivative of x and y square. So we will have local minimum and maximum if d is greater than 0. If d is less than 0, then simply there is not any local maximum or minimum. So the first condition you need to check is whether d is greater than 0 or less than 0. If it is less than 0, there is no local maxima or minima. We will check it is only if it is greater than 0. Now further classification is there. If d is greater than 0 and second order derivative with respect to x is greater than 0, then this will be called as local minimum. But if second order derivative with respect to x is less than 0, then it will be called as a local maximum. Now in case C, the point A comma B is called saddle point of F comma C, and there is no local minima or maxima in case of D less than 0. Let us see this example. We have find the maxima and minima of the function f of xy is equals to x cube plus y cube minus 3axy. This is a very important question. It is asked many times in our university examination. So now we have to calculate the extreme point of this. We will simply follow the process, find the partial derivative, first order partial derivative with respect to x, first order partial derivative with respect to y. When you are taking partial derivative with respect to x, y will be constant. When you are taking partial derivative with respect to y, x will be constant. So it will be 3x square minus 3ay. Take that first order partial derivative with respect to x equal to 0. Find the value for x square. Similarly, find the partial derivative with respect to y. Take the derivative equal to 0 and find the equation. So you can see. Now if you are putting here x is 0, definitely y will also be 0 and you will not get any non-zero value. So we have to solve it by using some other way. Divide the above two equation that you received here. By then you will get that x square upon y square is equals to ay upon ax. Simplify it, a and a will get cancelled. This is x upon y whole cube is equals to 1. Further taking cube root, x upon y is equals to 1, which means cross multiply here, which means x is equals to y. Now substitute this value in this equation. You will get that x square is equals to ax. Simplify. You are getting here two stationary point. One is x is equals to 0, another is x is equals to a. Put this value of x in this x is equals to y. The 2 points are 0, 0 and a, a. After this we have to calculate second order partial derivative with respect to x, with respect to y and with respect to x and y. For that we will again go back to our first order derivative. Again differentiate this equation with respect to x. This term does not have x, so this will be 0 and it will be 3 to the 6x. So f of x will be 6x, and similarly f of y will be, this will be 0 as it don't have any term having y, so this will be 0, treating as a constant. This will be 6y. So second derivative with respect to x is 6x, second derivative with respect to y is 6y. Let us see what is the derivative with respect to x and y. Now this is f of x. Take its derivative with respect to y. This term don't have any y term, so this will be treated as constant and this will be minus 3a. Similarly, if you are taking derivative of y with respect to x, this term will be constant and this will be minus 3a. So irrespective of the order of derivative, you can see f of xy and f of yx both are same, and which is equal to minus 3a. Now our further result will depend upon the value of d, whether d is greater than 0 or d is less than 0. So determination of Hessian is there. D is equals to multiplication of second order derivative with respect to x, multiplication of second order derivative with respect to y, minus f of x into y square. Put the value. This is 6 are 36, x into y minus 3 square is 9, a square. Now this value, definitely it will depend upon x and y. Put first point 0, 0 here and second point a, here. If you will put 0, 0 here, this will be minus 9a square, which is d less than 0. And as per the discussion, as we have discussed here, if d is less than 0, then there is no local maximum or minimum. So in that case, this is a saddle point. So if a is non-zero, this is less than 0 and this is a saddle point. What if a is 0? This has, so if this is 0, there is no local maximum. Now let us see this for second point, which is a, a. For that, put here x is a, y is a. A into a square, 36a square minus 9a square will become 27a square. Now a, it doesn't matter a is positive or negative. We know that square of any number is always 0, but it should be always non-zero. If a is non-zero, this is always greater than 0, right? Then What about second order derivative? This further decides our local and maximum, local minimum or maximum. Now further, if a is greater than 0, then second order partial derivative with respect to x will be 0 and this will become local minimum. But if a is less than 0, then second order partial derivative with respect to x less than 0 and this will become a local maximum. So if a is equals to 0, the point 0, 0 is the only stationary point and it is degenerate as f of value. So you can put the value here in the given function f of xy, put value point a, comma a. The given f of xy is equals to x cube plus y cube minus 3ax into I. At the place of x put a, at the place of y put a and calculate. This is 2a cube minus 3a cube. So this is equals to minus a cube. So this is the minimum value. So this is the way we use local minimum and maximum to find the maximum and minimum value of any particular function. Thank you, students.